Now we're going to talk about voltage, electric fields, and distance. And it turns out that these three things, voltage, electric field intensity, and distance, are all related. And here's how. Suppose we lift an object against gravity. So here's the Earth. And suppose here's some mass. And suppose we grab hold of this mass and we lift it up. Lifting it increases the potential energy of the mass. And the change in potential energy depends on how big the mass is, and it also depends on the strength of the gravitational field. Well, the same concepts apply electrically. If we have a charge here, let's suppose we have a negatively charged object, and we have a little positive charge here, and we want to lift it. We want to push this charge against the pull from that larger charge, the large negative charge. Lifting it against the electric field will increase the potential energy, the electrical potential energy of the charge. And the change in potential energy depends on the magnitude of the charge and on the strength of the electric field that's produced by this charged object here that we're lifting it against. Now those ideas we've already discussed, but there's one other factor to consider. Look again at the mass being lifted against gravity. The potential energy change, we said it depends on the mass. Bigger mass will involve more potential energy change, and it depends on the strength of the gravitational field, but it also depends on the distance. If we lift an object a certain height, the higher we lift it, the more the change in potential energy. And you probably remember the equation for potential energy. Potential energy is mgy, and this y here is our height. You could call it y or you could call it h. It doesn't really matter as long as you understand that it's the height. And the change in potential energy depends on the height. Well, that same concept also applies electrically. If you move a charge from one point to another in an electric field, the change in potential energy is greater if you move it a greater distance. And we can show how this all works out mathematically if we start with our equation for voltage and do a little derivation. So here's our equation for voltage. We said that voltage, V, is energy over charge. So I'll write energy over Q. Now energy is the same thing as work. And work, we have said, is force times a distance. That's basically our definition of work, the application of a force through a distance. So we imagine the force we're using to lift this charge against the electric field. That force times the distance that we lifted. So I'm going to say that energy is equal to work, which is equal to force times the distance. And I'll use a D for distance. And I'm going to plug that in right here for energy. So I'll say voltage is equal to force times distance over Q. Now remember, we also had another equation that dealt with the force on a charge in an electric field, and that equation was F is equal to Q times E. So if we rearrange this equation and solve it for Q, we get Q is equal to F over E. And I'm going to take that expression and plug it in there for Q. So I get V is equal to FD times F over E. And then I can simplify this. The F's cancel out, and that leaves me with D over 1 over E. That E down there is in the denominator of the denominator. And mathematically, that's the same thing as being in the numerator. So this is simply equal to D times E. And so voltage V is equal to this. And that equation is commonly written like this. V is equal to ED. And this means voltage. And voltage, remember, always deals with 2 points. The potential energy difference between 2 points. And the voltage is equal to the electric field strength E times the distance D, and that's the distance between those 2 points. Now, one warning here about this equation. This equation works if our electric field is uniform. That is, if the value of E here doesn't change appreciably over this distance d. Now that's not typically the case around a point charge. Around a point charge, the electric field intensity decreases according to an inverse square law. But if d is very small, then we can ignore that slight decrease from one point to another. Just like gravitationally, the farther we are from the Earth, the weaker the gravity is. But if I lift something from the floor of my room to the ceiling, I'm not changing the distance appreciably compared to the size of the Earth. So over a small distance, we could consider the electric field strength to be uniform. And also, between two parallel plates, we can consider the electric field strength to be basically uniform. Okay, so I have this equation, V is equal to ED, and I can take this equation and rearrange it and solve for E, and I get E is V over D. And looking at it this way is instructive. This tells me that electric field strength can be thought of as volts per meter. Electric field strength can actually be measured in volts per meter. Now earlier we said that electric field strength or electric field intensity was measured in newtons per coulomb. So it turns out that 1 volt per meter is the same thing as 1 newton per coulomb. And I'm going to prove that to you right now. Watch this. Imagine 1 volt per meter. And remember what a volt is. A volt was a joule per coulomb. So I could write this as a joule per coulomb per meter. And remember from way back in first semester that a joule is a newton meter. So this is a newton meter per coulomb per meter. And you see the meters cancel. And we're just left with newtons per coulomb. So 1 volt per meter is the same thing as a newton per coulomb. Electric field intensity can be measured in volts per meter or in newtons per coulomb. Those are equivalent units. And here's an example problem, which is a pretty straightforward application of this equation. An electric field intensity of 3 million volts per meter is needed to get a spark to form in air. In a typical spark plug, and this is a spark plug in a car, the spark gap might be around 1/20th of an inch or 1.27 millimeters. And so basically in the cylinder in your car, looks something like this. There's a cylinder and the piston inside, which can slide up and down, although it forms a tight seal around the sides. And as it moves up and down, this piece here exerts a force on the drive shaft to rotate the drive shaft. And in the top, in a hole here, there's a spark plug is screwed in and tightened down with a bolt. And wires come in here, provide electricity to the spark plug. The spark plug goes down into the cylinder, and there's 2 little wires that come together. If you magnify that, you've got one here, that's a wire, and another one here, like this. And voltage is applied across these 2 points. So there's a voltage between 2 points, and that's this point and this point. And if you get enough voltage, you get a little spark right there. And that's right in here. And that's the spark that ignites the gasoline. And there's valves in here to spray in the gasoline and some oxygen and to remove the exhaust once it's burned. But the spark plug, a spark in that spark gap creates a spark to ignite the gas. That's what's going on inside the spark plug. So here we're just asked what the voltage needs to be to create the spark. Well, we can just apply the equation. Voltage is electric field times distance, and we're given both of those values. 3 million volts per meter. That's 3 times 10 to the 6 volts per meter times the distance of 1.27 millimeters. That's 0.00127 meters. And you can see the meters here cancel. And you just do the multiplication, and it comes out to 3,810 volts.